5105? So it says, draw the null hypothesized sampling distribution for each, label the 7 positions of the sample statistic, shade the appropriate region that models the p-value, then calculate the p-value, show the calculator command. Okay. Is that the right page? I hope. All right. So it says, we theorize, oh, this is a good one. I've talked about this one a few times. We theorize that coins actually generate heads more than 50% of the time when flipped. We choose to flip a coin 100 or 1,000 times and record the results. We obtain 50.4% heads over those 1,000 tosses. Okay, now, friends, does everyone admit this is a pretty boring activity? If you're going to go flip a coin 1,000 times, that's boring. But we'll see what we can generate about this. All right. So for problem number 1, let's just draw ourselves a normal distribution. Okay. So we all think that 50% of the time should be a coin toss. Agree? So then we're going to we have to figure our standard error out. And so standard error is probability, 1 minus probability over the number of times. So 50% is 0.5. 1 minus 0.5 is 0.5. And we'll divide that by 1,000. And if we do this correctly, it should come out to 0.016 is our standard error. And again, remember, we're putting the standard error in place of the standard deviation because we're dealing with a sample. Okay? So this is the same thing as 1.6%. Agree? Bless you. All right. So this would be like 51.6. This one would be 53.2, I believe. These are all percents. And then 54.8. And then if we subtract that 1.6%, so we get 48.4%. We get 46.8% and 45.2%. Okay, everyone feel good about that? Yes. So they claim that we had gotten a 50.4% heads with 1,000 flips. Okay, so 50.4 is like here. Okay, so and they're saying that more of the time. So this is basically the shaded region that we are looking for. Okay, now we don't have to create a null. We don't have to do anything like that, but we do have to figure out our p-value. Okay, so the p-value is definitely one you want to jump onto Desmos to start figuring out. So normal distribution, and we're doing 50, 1.6. So here's our normal distribution based on this. So then we want to do our 50.04 or greater. All right, so we come up with a p-value of 0.4. Okay, so what do you think, friends? Was this just dumb luck that this happened? Or is this showing validity that our coin is really bad? Our p-value, so normal p-value, you want it to be less than 0.05, agree? Is 0.4 bigger than 0.05 or is it smaller than 0.05? It's bigger. So we have to, it doesn't ask us to do, but this would be fail to reject the null hypothesis. Okay, fail to reject. Meaning, heads, tails, not equal to 50%, so fail to reject. Okay, if it was smaller than 0.05, then we would have to accept or reject the null. So we're not rejecting the null. All right. It is known, Oh, number 2. It is known that the gas mileage of a Ford Fusion is 32.8 miles per gallon on the highway. No way. Okay. We theorize that higher octane gas will increase this mileage. Oh, yeah. We collect 30 random Ford Fusions and run each on a tank of gas. We discovered the gas mileage of these cars is 33.9 with the better gasoline. No way. Okay. Well, that's what they're saying. I will assure you that, my friends, if you choose to go to the gas station and fill up with anything more than just the least expensive unleaded, you're pretty much wasting your money. Okay, just what I have seen. Okay, that's supposed to be a normal curve. I'm not trying to make it skew left, but I did. So I have 32.8, which is our middle. Okay, we want to find our standard error. So a standard error is going to be the standard deviation that they gave. Did they give us a standard deviation? 4. Where is it?
Standard deviation of 4. 32.8 miles per gallon on the highway with a standard deviation of 4. Yes.
Oh, gotcha. Okay, so standard deviation over the square root of the sample. So standard deviation you said was 4 over square root of how many cars we test? 30? So 4 over square root 30 comes out to roughly 0.73. So if we do our normal curve, add 0.73 each time. So we're actually going to make that, we're going to just make that 0.7 just to be, so 33.5 and then 34.2 and then 34.9 and then subtract it. So 32.8 minus 0.7 is 32.1. 31.4 and 30.7. Okay. And then they said that this the new gas or the good gas is going to give us 33.9. Is that what they said? So 33.9 is like here. So does that look like it's far enough away? So we're basically shading this region to the right, okay, because we're hoping that this new gasoline did something good. So things that might have affected gas mileage other than the new gasoline. You might have had like the ideal operating range of temperature. You might have had your tires overinflated, so you didn't have as much friction coming from your tires. So those are all things. So we're going to jump on Desmos, see what we do. So 32.8 is going to go here. And 0.7 is there. And we're saying that it's better than 32.8. Or wait, 33.9, excuse me. Okay, so
Did you put 0.7 as the
standard error, right?
Yes.
Yeah, okay. So this has a p-value of roughly 0.06, roughly. Did I do that right? Oh wait, I'm off. 30, is it 33 point? Yeah, 33.9. We're good. All right, so we have a p-value of 0.06. 0.06 is still bigger than 0.05. Agree?
Yes.
So in this case, we would have to fail to reject the null in this case, but that's basically p-value. 0.06, huh? So it's close. I would say things that you might want to change in this situation, you might want to do another random sample. You might want to increase your random sample. You might want to try it at different temperatures. I mean, all these different, there's lots of variables we can put in place. And then it says number 3 says a professional athlete takes an average of 220 days to recover from an ACL tear. Ooh, ouch. With a standard deviation of 40. Okay. Medical researchers are attempting new treatment that will reduce this recovery time. Sample of 64 professional athletes were obtained. For this study, the average recovery among this group was 206 days. Okay. So someone has a new plan on how to help the athletes with the torn stuff in the knee. So normal distribution. Okay, so we thought it was 220 days. They gave us a standard deviation of what? 40? Okay, so we have to figure out our standard error, which is the standard deviation over the square root of the sample size, which in this case is 64. So that's going to come out to 5, I believe. So that means you got 225, 230, 235, 215, 210, and 205. All right. So they had said they found something that at 206 days. 206 days recovery is what we had, this new thing had done. So 206 is like here, so we're thinking 206 or less. Ooh, that's kind of far from the mean. This new sample might work. Okay, so normal distribution, 220. So we got 220. Standard error of 5. And we're going to say that they found 206 days. 206. Oops, I went the wrong way. That should be negative. 206 over here. Ooh, we get a p-value of 0.002. Is 0.002 less than 0.05? Very much. This means, so basically your null hypothesis in here, there's no difference in treatment, and the null is we found it's less days of recovery for our alternatives. So this case, because our p-value is smaller than 0.05, we reject the null. So guess what, folks? These doctors are on to something. That might be something you actually find in a medical journal. I mean, if you're ever really bored and you want to read some really dry stuff, I mean, it has all this stuff in there.
Steph, can you go back to that drawing page?
Yeah.
I just wanted to get that shaded region.
Shaded region?
Yes.
That little tiny blue. All right, this one says, currently it is known that 16.8% of adults smoke. Oh, shame on those smoking adults.
Wait, how many percent?
16.8.
Crazy.
Is the percentage lower in Colorado? Well, I don't know. We plan to survey 500 adults in Colorado. And that makes sense that we had sampled 500 adults in Colorado because we think that Colorado has a lower smoking average. Agree? Assume the results of the study showed 17.1% smoke in Colorado. Ooh. Gosh, we thought we were onto something, but we were bad people. All right. Bad smokers. All right. So it says establish the null and the alternative. So smoking equals 16.8 or 16.8%. And then smoking is less than 0.168 or 16.8%. Oh boy. All right. So is this one or two tail?
One.
One tail. Okay. So, and I'm just going to put that we have less than. Okay. So we're searching for lower. Okay. Let's assume that the researchers are more concerned about a type 2 error. Oh, wait. Does that say that? Type 2 error. Type 2. Okay. So type 2 is reject. Oh, shoot. I just lost train of thought. Type 2 reject or fail to reject? Oh, man. Is it fail to reject?
No, type 2 is fail to reject the null.
So fail to reject the null.
But
Fail
the alternative is actually true.
fail to reject the null when it is false. Okay. Okay. Ooh, so they're concerned about a type 2 error here. Okay. So let's assume that they're concerned about type 2 error. Should they use a higher level of alpha or a lower level of alpha? So should alpha be higher or lower? Okay, so let's think about this. Okay, so type 2 error is fail to reject the null when it is false. So we want to make a higher alpha. A higher alpha raises the chance of a type 1. So if this is higher, this raises the chance of type 1 error. So if it raises the chance of a type 1 error, then it lowers the chance of a type 2 error. Okay, so that's, ooh, make note. Maybe put a star next to that. That might be something that we might want to take a look at. And number 7 says, without calculating the p-value, researchers already know they will fail to reject the null hypothesis. Explain how they know. Okay, so they're saying that they already know that they're going to fail to reject the null. Okay, they already know they're going to do that. The reason then that they know that is our sample stat, our statistic, was 17.1%. Which is greater than the alternative, than HA. All right. So that's kind of wish-washy, but so I think, I mean, so I imagine that from certain surveys that they would have figured out a 16.8% nationwide, and then if we survey the Coloradans and we find 17.1%, so they're failing to reject the null because the statistic that we found of our sample, 17.1%, it contradicts the alternative. Okay. Yikes. So someone better go do another study. Okay. So think about this. If you were a prosecutor and you know because of information that you can't really use in court, you know the person is actually guilty, you're digging deeper into other resources to verify that they are having that guilty. Okay, that happens in court a lot. That happened to me in court just this last time. What did they tell us in the beginning of that whole court case? This guy was up for his 4th DUI. And they said, yeah, on this date, it was his first one, he was guilty. The second one was on this date, he was guilty. On the third one was this date, he was guilty. And then they say this to us, but you can't use that to show a pattern of events. You have to ignore that. And it's like, you told us as a jury. Like, you guys are crazy. But, oh, that jury duty. Oh, I'll tell you. And I served my time. Served my time on the jury. Got released because I used statistics to get me out of it. All right. This one says, currently 62% of movie theater goers buy concessions, soda, candy, popcorn, etc. I personally like the nachos with the fake liquid cheese and the jalapenos. That's Stirrup's go-to. All right. The theater owner wants to increase this percentage with more employees. Perhaps people don't like waiting in lines. They're like, heck, I'm just going to the movie. I'm not going to buy stuff. So they decides to hire more employees, thinking shorter lines will produce more sales. But then you have to pay those people. So who knows if it really works. So assume a random sample of 100 customers showed 67% purchased concessions. And the researcher chose an alpha of 0.08. Oh, they're changing their alpha from 0.05 to 0.08. Okay. Sketch the null hypothesis. All right. So this is number 8. Let's see if we can make ourselves a normal distribution best we can. All right. So our middle is 62%. All right. So now we have to find the standard error. Standard error, this one's in percents, right? So we have to go percent, 1 minus percent over the sample. So the percent that they were using, so currently 62%. All right, so we're going to go 0.62, 1 minus 0.62 over 100. If we do that math, we find our standard error is going to be 0.05 roughly, which is 5%. Okay, remember we use the standard error in place of the standard deviation because we're dealing with the sample. All right, so that'll take me to like 67%. That takes me to 72%. That takes me to 77%. This takes me to 57%, 52%, and 47%. All right. So they showed 67. So we're talking about 67 being right here or greater. So we're going this way. Okay. So calculate the p-value. Remember, this guy decided to have an alpha of 0.08 versus 0.05. Okay, so that's what we're testing against. And let's figure out our p-value. So Desmos time. This is so exciting. What do you guys think? So 62 is here. 5 is the standard error. Look at our thing. And then we want 67 or higher. All right, so it looks like about 0.16 is our p-value. So we got a p-value of 0.16. 0.16 is bigger than 0.08. Okay, so since we are bigger than that 0.08, we are going to, this is bigger than 0.08, and that means that we are failed to reject the null. Okay, and we didn't find strong evidence against null, which we didn't even list the null, but which is 62%. Cool. So why did this employee, or why did this boss realize, oh my gosh, if we have more employees that we increase to 67%? There's variables that We might not know. It might have been really hot outside and people all wanted to have a Coke, right? All right. So, hey, so you're gonna make sure your name's on those. We're gonna hand those in. Hey, did all the papers make it all the way around the room? Did the homework make it around? Who has the homework stack? Oh, there. Okay. So tomorrow I'm going to give you back the quiz that I wanted you to take on Friday. Some of you were able to start that. Some of you might think you're done, but you might want to go back and double check. And then if you didn't start it, then you have the opportunity to do it as well. I got you. Homework.
Just so happens. Come on, good. Come on.
Homework. Yay. These are all the extras.